In this section, we're going to explore the realm of stereovision. Stereovision, stereoscopic vision, is what allows you to perceive depth, what's referred to as depth. But it's a little bit of a misnomer to say that stereoscopic vision just allows you to perceive depth. Obviously, there's a lot of things that allow you to perceive depth aside from stereovision, and we'll go over some of those cues too. But the point really is that you perceive a three-dimensional world based upon depth perception from stereoscopic vision, from other cues, from form perception, from motion, and so on. All these are integrated into one three-dimensional model of the world that includes your body in its shape and form and how it interacts with that three-dimensional model, so that when you move in that space, you move consistent with a model that's accurate. It's built on vision, but it's also some other senses actually do factor into it. Hearing does to some extent, and of course, just navigation by touch can often allow you to explore a three-dimensional environment. But what your brain does is it takes all this information, it creates a three-dimensional model, and that becomes the basis for your navigation through the world, for your perception of the world, in terms of how far away things are and what their height is, what their width is, and so on. And it is the fundamental model that largely your right hemisphere constructs. Well, here in this first one, we see a bug, a microscopic image of a bug, done in the anaglyph format, which I'll get into some detail a little bit later. To see this in 3D, you need anaglyph glasses. And what the anaglyph glasses do is separate the image into a left and right view, as your eyes would see it if you were actually looking at that object. And your brain then constructs a three-dimensional representation of the object that includes a third dimension, includes depth. So I've sent a link. There's a link at the website to a place that sells some free anaglyph glasses. You may have them for other reasons. I've seen them also for any kind of 3D comic books, 3D advertising, three-dimensional, anything that deals with book content that includes three-dimensional stuff will often have anaglyph glasses. I've even seen them on cereal boxes, because they'll show three-dimensional images on the box. You can make your own if you have the red and the cyan or red and blue clear plastic. Just make what looks like glasses, and it will separate the image just fine. If you go to the course website, though, you can see a link there to get some free glasses. It's nice to have these glasses because you'll be able to see the 3D images that are throughout this presentation. The basis for stereoscopic vision, contributing to depth perception, has to do with how your two eyes produce a slightly different retinal image and the integration of this slightly different retinal image by your brain. Well, if you move your eyes about, you're going to have clues to depth perception by how your eyes have to move and also how your lens has to focus to cope with the depth, how far away an object is. And here you see the representation of that in graphic form. So you see where your eyes can move, they have convergence, and so if you're, think of looking at something really close to you, like put your hand up to your face, and your eyeballs are going to have to converge on that close object. If you look far away, your eyeballs are not going to be so converged, they're not going to be so together, they're going to be more parallel in the field they create. So the degree to which you have to converge your eye, and it can make convergence of your focus to see an object close to you versus seeing objects that are far away represents a cue that can be used to tell how far away something is, tell what the depth of that object is. I'm not so sure. This must be done implicitly. I have no idea that I'm doing this when I look at objects. Probably there are eye movement cues as to how far away an object is that is just implicitly, unconsciously part of the visual processing system, and it's not really understood how it's actually incorporated into the 3D model. But when you look at an object far away, obviously your eyes are a different configuration than when they're close, and the convergence of them is referred to as the horopter. That's the ideal sort of convergence for your eyes to fixate on an object. Okay, here's another clue that might be used by the system. Whenever you focus your lens on an object, remember your lens will get thin or squat, it'll go back and forth there, up and down, to focus on an object. When you accommodate to an object, your muscles of your lens are going to be either contracted or they're going to be relaxed, depending upon how far away the object is. Just like in a camera lens, when you focus your camera, You move the lens in and out. Now, of course, a biological lens in a human eye, it's done by distorting the lens shape. But the degree to which those muscles have to contract to distort the lens is a cue as to how far away the object is. Again, this is one of those that must be done implicitly. I have no sense at all that I'm getting information from my lens about how far away objects are. I certainly have a clear understanding of it. If I look at an object and bring it really close to my face so it's out of focus, my lens is really trying to accommodate so I can see it. As I move it further away, my perception becomes sharper. My lens accommodates to that distance, and I can see it clearly. So obviously the distance that the object is from my eye, from my lens, is a clue to how much the lens has to accommodate. It's a clue to how far away it is. It's a clue to how far the depth is away from me. Now you have a number of monocular clues to depth perception. Obviously a real simple one, which I'll get to in a second, is whether one object is in front of another object, if it occludes it. So if I'm looking at a scene in which the foreground object is occluding a background object, obviously the background object is further away from me than the foreground object. So that's a monocular clue, a very strong one, that there is depth to that image, and it's a strong clue as to how far away objects are. Another is linear perspective. As you see here, if you think about perspective, parallel lines, for example, when they're going off into space, appear to converge to a point. And that's just an artifact of our vision, or using a lens to perceive light. And we have this perspective model. So objects that are further away from these, say these railroad tracks here that you see in the image, you have two parallel railroad tracks going off in the distance. And if you have formulated a three-dimensional model that includes how close the lines have become relative to the distance they are away. So right now I'm looking at it, I'm thinking the train that's way off in the distance, not only is it small, but it's also at the point at which the tracks themselves appear to converge. Well, this is an interesting illusion. This is actually an optical illusion, where you take two bars like this. The bar in the front is separated. It's a distance from the railroad tracks. The bar in the back overlaps them. Well, now your brain's got a problem here, because are the two bars going to be the same size? Well, if that bar is truly far away, then it should be larger. And so your brain says, well, if perspective makes it that far away, it must therefore be a large bar because it's covering the railroad tracks. Whereas the one in the front here, since it's not covering the railroad tracks and it's close to me, can be of a certain size that's smaller, when actually both these bars are the same size. Now you can see your brain has distorted perception in order to make it internally consistent. Now fortunately in the real world you don't have objects like this that are artificially distorted. This is just done in a two-dimensional representation of the scene, but your brain has constructed a three-dimensional model of that scene. As long as those bars are in it, it's going to fit them into the three-dimensional model some way, even if it has to distort the size perception to make that happen. Here's another monocular clue here. Now what's actually on this page, on this graphic, is just circles and ovals, but they're placed in a configuration that it makes it look like a three-dimensional structure. It looks like waves with shadows. And my brain has reconstructed that display to be a three-dimensional shape. This becomes a strong clue as to to depth. I have an estimation of how far away the back wave is from the front one. And the size gradients of these ovals, it becomes a very strong cue that I've got linear perspective working here, and I'm looking across a three-dimensional shape. Now this is not a stereoscopic clue. This is actually a mono clue that has to do with the size of objects, very similar to the linear perspective clue that I showed you before with the railroad tracks. Another clue is the height of objects in the visual field and where they are relative to other objects. So as I'm looking at this scene here, the height in the visual field tends to indicate depth away from me. So objects that are away from me tend to be higher in the visual field than objects that are close to me. And so when I look at these three figures here, these three forms of a man, I have a sense that the one that's down below to the right is closer to me than the one that's up there on the left. Now, I've only constructed that because of its height in the visual field. And I've also, I think, used the horizon line as a way of forming a surface, and that surface would include people going off in the distance. Unless they're floating in the air, and I can imagine that too, I guess, they would not be at the same plane, three-dimensional plane. I clearly have a sense that there's depth in this image, even though it's actually quite shallow. That's just produced by the height of the characters in the field and my expectation for where they should be relative to how far away they are. Yet another clue is provided by shading and contour. We expect light to fall on objects and form shadows, and shading and texture consistent with how light falls. And these shadows and these contours produce an illusion of depth, because shadows, of course, they fall away from the object. So the degree to which they are fallen away produces a perception of depth, a perception of a three-dimensional structure, and then we formulate that into a model of how far away and how close things are. So as I look at this model here, this looks like two sort of holes, indentations in the ground that have shadows consistent with the sun being up in the right, toward the right, and obviously high off the ground. It's producing a shadow on the edge and some glare on the dimple in the bottom of the indentation. And I have a sense of how far away those objects are in their shape by how that shadow has formed. Now, occlusion, of course, is a strong cue to depth perception. If I have an object in the foreground that's in front of another object and obscures it, occludes it, then I clearly have a sense that the object in the foreground is closer to me than the object in the background. Now, here I've given you an example of the Dalmatian again. That was used to represent also how movement influences form perception. But it's also a good example of how figure and ground work together. When the dog is walking across the movie, you clearly have a sense the dog is in the foreground, and the texture in the background that's very similar to his fur, texture, is in the background. And so your brain, when it sees that movement and sees that occlusion, forms a very clear model that the dog is closer to you and is in front of some sort of background that's further away than the dog is. And this occlusion produces a very strong clue, and it's got to be one of the most important ones that we use. Obviously, if an object is in front of another object, that's a strong clue that it's closer to you than the object that's in the background. Another monocular depth cue is atmospheric blurring, especially when you're looking across the great expanse of landscape. Obviously, there's a lot of atmosphere between you and mountains that are far away. And whenever you see water vapor in the air in particular, water vapor will tend to turn the color palette, or tend to shift the colors from the full range of colors in the foreground to a blue shift in the background. Now, you're probably not really aware of that unless you're a painter or something, that there's this shift of color. But the next time you go out and see a landscape, look at it, and you'll see that the background mountains or far away is bluish or greenish, and the foreground has the regular set of colors. Now, painters know this, and what you see here is a photograph of the top right from your book that has the atmospheric blurring in it. It doesn't depict the color shift, but clearly when there's more atmosphere between you and the mountains, there's also a diffusion, a blurring of the image. And then down below you see a painting by Thomas Moran, a Hudson River School painter, a landscape painter, who used this to depict the mountains as being close to you or far away. Clearly he's got a very, much more interesting looking atmosphere. But you can see the clear blue shift that he uses. When the mountains are farther away, not only are they obscured by some mist because of the atmosphere that's between the viewer and the mountain, but also because of the water vapor shifting the color, it shifts it into the blue range, and you can see clearly the background is more bluish than the foreground. Okay, the final depth cue I'm going to review is referred to as motion parallax. And parallax refers to different images on your retina depending on how your eye is positioned. And as we walk along, as our eyes move in space, near objects are going to have a different parallax. They're going to have a different impression on the retina than far objects. Notice that is this eyeball. This is a schematic here of one eye as you move it back and forth. You can see where object A, or position A there, is going to have a different location on the retina. at position 1 than it does at position 2, which is very different than the locations of position 1 and 2 for object B. Objects that are far away from us tend not to move around on the retina very much. As you look at that visual scene, they tend to, and move, as you're looking on the visual scene, they tend to stay in the same place. Notice that B1 and B2 there are roughly the same place. They're on opposite sides of the retina, but you can see where they've not moved very much. Whereas A1 and A2 are very big difference, very big changes in their location as your eye has moved around the object or back and forth across from the scene. So objects that are far away tend to have a much more constrained movement on the retina than objects that are close to us. And that becomes a powerful cue as to how far away objects are, how close they are. Okay, well, the major way that we get information to perceive depth has to do with binocular vision. It explains why your eyeballs are in the front of your head facing out, and they seem to be redundant, in picking up parts of the visual field. You could probably get along fine with just one eye seeing the visual fields, but for some reason you got two. Well, having two turns out enables a very interesting mechanism by which the two images are combined to produce a cue or data about the depth of the visual field, how far away objects are. And it's a very interesting process. It's still not completely understood. It basically has to do with correlating two separate pictures that you get from each eye in a way that allows the brain to abstract depth information. Now, let's start with a very simple demonstration. What you want to do is just put your hand in front of your face and look at it. Close one eye and then the other eye. And as you do this, you'll notice that your hand's image changes. Each eye is going to have a slightly different image of your hand than the other one. These slight differences are cues to the depth of the how far away your hand is from your face. And your brain takes that information and formulates the three-dimensional map, the three-dimensional space that includes your body, that it occupies, and it constructs for you of the world. Now, the clue is derived from each image from each eye. Okay, well, suppose we wanted to create pictures that have three-dimensional depth to them. We have to replicate that somehow. We have to figure out some way to replicate how your brain is getting information from two independent eye sources. So what humans have invented, what people have invented, are stereo cameras. And you see one on the slide here. Now, you probably don't own a stereo camera. You may never have actually seen one before. Stereo cameras are kind of a specialized area of photography. It's a very popular specialized area, but it is something that is very specialized. And stereo cameras have existed for a long time. They were certainly in place when the earliest photographic processes were invented. Now, what happens is you have a camera here that's got two lenses. Now, each lens has its own, it's going to expose its own part of the film. And these lenses are exactly the same distance apart as most people have their eyes apart. So you can imagine these as two eyes. They're each going to take an independent view of the world that has the same difference, and this difference is referred to as parallax, that has the same parallax as your eyes do. So it's going to replicate in a pretty similar fashion what each of your eyes will actually see. So imagine it takes a picture of those figures up at the top there. Now the left eye is going to, the left camera lens will take one image. The right camera lens will take another image. Now the way to combine these in a way that you see them independently. Now what I want to do somehow is figure out, okay, how do I get the image that was taken by the left lens into just that image into your left eye? How do I get the image just from the right lens into just your right eye? Well, obviously, if I just printed the film, you'd look at it and it would be going into both eyes. The image would not be separated this way. So what was invented was this method of using colored filters to separate two images so that you see them independently, or your brain does, and it formulates a 3D image. Now, each of the two images are printed on a piece of paper in these two different colors. So the image from the left eye, or the left lens, it's going to go in the left eye, is printed as red. Is the red part of the figure at the top there. The image that's going to go in the right eye is printed as cyan, or that bluish green color. Now, if you look at the glasses, they're not really configured that way. The cyan lens is on the left eye, and the red lens is on the right eye. But that, see, you haven't factored in the part about filtering. When I show that picture of the red and the cyan image through the glasses, so when I show the picture through the cyan glasses are filtering out the cyan part. So all that's going to be uniform. So you imagine the glasses, which they're transparent filters, all the cyan parts of that image are just going to be continuous. It's as if they aren't even there. Because there isn't going to be a white background. It's going to be a cyan background because the filter is cyan. So what you're going to see in the left eye is the red parts. So the red parts of the image are what's going to go into the left eye. Now that was taken with the left lens of the camera. Now just the opposite occurs with the red lens. The red lens is going to partial out the red parts. They're going to be made essentially invisible because the whole image is going to be red. And all you're going to be able to see is the cyan parts. So the cyan parts of the image are going to go into the right eye. And this was the image that was taken with the right lens. The lens on the right side of the camera, as if it was your right eye. So by using these filters, I've been able to expose your left eye to what your left eye would see in parallax of that image, and given your right eye what your right eye would see in that image. And your brain's going to take these two images as if you're looking at that object in the real world, not as a picture, and it's going to reconstruct a three-dimensional representation using the information from the parallax. And in subsequent slides, I'm going to go into how this happens and give you more examples of the anaglyph process. Now, the anaglyph process can only display black and white images well. You can kind of color tone them with other colors, but you can imagine if you're looking through these images through red and green glasses, you're not going to appreciate very well the colors that are in an image. However, have seen some color tinted or color printed images that also have the red and green color to indicate the parallax, and it works okay. It's just that it's not as clear as black and white images. For example, some of the animated movies that were done with 3D modeling on the computer were done so that you could use anaglyph glasses to see them as 3D movies. Now, see, it could be very easy to do this with a 3D modeling program because instead of a camera, you've got a computer. You just tell the computer, okay, render that movie, 2 inches where the camera's, 2 inches to the right. And then you get the other eye. And then you combine those in a multiple print of the movie that has the cyan and red distinction in it. Okay, well, anyway, in subsequent slides, we're going to go through some more examples of these, and I hope you've been able to get some anaglyph glasses to look at these. Otherwise, they're going to look very flat. But it's amazing when you look through the glasses how they will pop right off the page and look like a full 3D representation of the object. Okay, here's an image of some squirrels. And when you look at these with anaglyph glasses, they jump right off the page there. Again, this was taken with a stereo camera. With the left image, the red one is done with the left lens, the right one is the cyan one. And when you combine these, you get this interesting 3D picture of these squirrels. Now notice that the parts in the middle, and essentially the middle parts of the visual field, tend not to have much distinction of red and cyan. They're the gray parts in the image that aren't really separated by the colors. They're seen as pretty much just the texture of the object, where the depth of the object is a combination of monocular cues, because if you look at this, you can see where some squirrel parts are occluding the other squirrel, so that squirrel's got to be in front of the squirrel that it's occluding, and other monocular clues in there like shadows and things like that. All this is combined with the parallax to produce a 3D image of the squirrels. Here's another image taken with a 3D camera. These images are nice if you have objects clearly in the foreground and then objects clearly in the background, like you see here. So the riders in the front and the left there are clearly seen as very much in front of the other characters, the other objects in the scene. This makes a nice stereo image because if you have everything in the same plane, you won't really get a depth effect. It'll look like everyone's pretty much at the same level. Okay, here's one made with a computer program, a 3D modeling program. Now what the modeler has done is create this little character here in a 3D model, like I showed you before in one of the other presentations. So you can see how these primitives have been combined to make this little character here. So you see a cube back there, and of course his head is a sphere, his body's a sphere, and his eyes and so on, all these little spheres, little cylinders for his antenna, and little half spheres for the tops of his antenna. Well, what you do with a computer model is you make the first model of him looking like this, basically, and you save that image. So you save that, you take a snapshot of that image, and you would save that, say, as the red side of the image. Then you move over the amount of space you need for the space between the two eyes. You move the virtual camera over. Now see, all these 3D models have a virtual camera, they have virtual light sources, and you have a camera which represents the image you're looking at, or the point of view you're looking at. You move that over 2 inches, or whatever the distance is between the eyes. It's got to be very carefully done. It does have to be really match the distance between the two eyes, which I don't remember off the top of my head what exactly that number is. If you don't do that, it won't be perceived by the brain correctly, and it won't be interpreted as a 3D image. At any rate, you move the camera, the virtual camera, over, and that changes the perspective of the rendering of the model. So it represents the parallax of the right eye. Then you take another snapshot. You take another picture, just like you were using a stereo camera. You save that then as the cyan image, and that becomes the two images that are combined. You then blend them together, using Photoshop or some other graphics program. And then you blend them together like you see here, so that when you look at these images with anaglyph glasses, you see a 3D little creature here. These can often be much more effective as stereo images than ones actually taken with a stereo camera. And the reason is because the rendering is done so accurately. So stereo cameras, the objects, are moving and things like that, and it produces some blurriness. Here you can be very, very careful about the stereo effect and produce a very accurate 3D rendering. Here's another interesting anaglyph image of the moon. And you can see in this image the almost equal representation on the right and left of the cyan on the right and the red on the left. That's because this object is essentially a sphere. And so you have an equal representation of each of the parallax on each side of the image. Here's a random dot pattern that looks like, when you look at it in 2 dimensions without the glasses, it looks completely like a pattern of random dots. And then when you put the glasses on, you see where there's a pattern there. There's structure there. But you can't see it without the glasses. It's an interesting demonstration of the same effect. Clearly here the 2 parts of the image are being represented in the dot pattern somehow, but you don't get to see it until you actually wear the glasses. Here's another 3D image that you may have seen in shopping malls and books and things. This is a variation of the random dot stereogram that was invented back, I think, in the 1960s or so. They came out as a popular graphic, I guess, in the 80s, 1980s. And they've kind of died out now, but I remember going around shopping malls and seeing these all over the place. These are representations of the 2 images. Now remember, whenever you're going to have stereo vision and depth perception, you're going to be somehow presenting the 2 images to the person. It's just that here it's done in a way where the 2 images are presented when you sort of cross your eyes. Now if you think about it, when you cross your eyes, you're overlapping 2 images from each eye. And this process utilizes that to present 2 images to you. So if you look at this image and try to look past it, where your eyes accommodate to a spot past the screen, you should eventually see the 3D image pop out. This image just shows sort of a ridge and then sort of two valleys on each side of the ridge. And it's very vivid. It's a very strong image once you see it. And once you see these images, it's very easy to see them in the future. You have to get used to the method of sort of crossing your eyes slightly or accommodating past the image. Here's another method by which stereo views are made. In this method, you have a stereo camera just like before. You take the two independent images in the left and right eye, and you print them as you normally would, side by side. You then have a device that takes the two images and through the action of prisms. Now see, these devices were very popular in the 19th century. I think most people think of them as just some kind of a viewer. These are just lenses in here. But what was actually in the viewer are prisms. And the prisms remember prisms bend light. So prisms bend the light of each image so that the one on the left goes into your left eye, the one on the right goes into your right eye. And since they're the independent images taken with a camera, your brain combines them into a 3D picture. These are not very popular now. If you go to a flea market or antiques mall, you can find lots of these viewers. They were very, very popular in the 19th century. As entertainment, people would just get these pictures and look at them for hours on end. And all kinds of viewers were made. They were very, very popular. Actually, the Keystone Company in Pennsylvania was a big producer of the stereo pictures. And they produced stereo pictures of everything you could imagine, from comic scenes, funny things, plays, obviously travel, famous places. There was a lot of scenes done of the world wars, especially World War I, where there were probably thousands of stereo pictures made illustrating that war. They were very, very popular. Some of the stereograms, of famous people and things like that, or famous events, are now very valuable. There are even stereo daguerreotypes done using that really old method in which there is no printing. It's done by a process of actually exposing a metal plate. At any rate, this is the other method. This is the other way it was done. This takes the two images, instead of combining them by using the anaglyph method or something like that, using filters, it combines them using prisms. Now, the great advantage of this method is that you can make color images, make color stereographic images, and that's a great advantage. They just don't have to be black and white. Unfortunately, color photography wasn't developed very well at the time in the 19th century. Color photography was probably made, reliably made in the 1950s. And so the color photography wasn't around, but what people would do is they would paint these. They would color these to give them color, and that's how they would add some color interest to the pictures. And you can see them clearly, the 3D objects, in the colors that they paint them. But here, what you've done, the same thing. You're presenting, each independent eye's image to each eye, as if you were looking at that picture of that column, of that arch there, as if you were looking at that image in real life, and your brain combines the two as if it had real parallax to deal with, and makes a 3D picture out of it. Another modern application of stereo vision and stereoscopic vision was the development of holograms. A hologram is a photograph that is built using laser light, in which the two images are continuously presented to you as if there's absolutely no seam at all. So that when you look at a hologram, it looks in 3D continuously, no matter how you tilt it. And the 3D information, the parallax, is embedded in the photographic process using these lasers. Unfortunately, I can't depict one in a PowerPoint presentation or a slide presentation like this. You actually do need to see the actual object. You have probably seen them. They're pretty popular. For quite a while, they were being sold in retail as decorative items. That's died down quite a bit in recent times. You see a lot of holograms as security tags. When you buy something from the NFL, it will have the NFL hologram on it. That's what these companies went to, because the making of holograms for decorative purposes just wasn't working out. They weren't making much money. Obviously, if they can make thousands of little holograms for labels, they can make a lot more money doing that. And also, one of the companies that was providing the film, they need a special film to make holograms, decided not to make it anymore, and so all that was left was the remaining stock of film. This one here was a nice Polaroid demonstration hologram that had two images built into it, so that when you turned the image, you saw a picture of a brain. Then when you turned it the other direction, you saw the skull and the eyeball here emerging. That's done through multiple exposure holography. It was a pretty complicated method. This was also done with a film that had a very high resolution, very clear picture on it. These you can buy on eBay if you want. You can run into them on eBay. Probably thousands and thousands of these were made because Polaroid wanted to demonstrate the process, and people kind of stocked up on them, and they couldn't sell them individually in the stores anymore, so they're selling them on eBay. You can probably buy 100 of them at a time if you want. At any rate, holograms use the stereoscopic effect in which the imagery is embedded in the film in such a continuous, smooth way that as you look at it, you see parallax constantly in the way the picture is being presented to you. It's too technical really to go into how they actually make these, and actually some of the processes are proprietary and kept secret so that other hologram makers won't figure out how it's done. The silver ones that you see, the image is actually made through small little etching indentations in the silver. It's not a photographic process. That process turns out to be very efficient to produce, and so you see all the tags and everything as the silver holograms. Really fancy glass plate holograms or really fancy film holograms like you see here, they're not used for the they're not mass produced for security purposes. If you take out a credit card and look at it, you're looking at one of the silver holograms, and the little hologram that's on your credit card is there as a security device. It's very hard to produce that hologram unless you got a lot of specialized equipment. You could do it, but it would be almost not worth the trouble, since it would be so easy to trace back who had equipment like that and why were they producing holograms that looked like the holograms on credit cards. So it actually has worked as a good security device. It's an interesting way to make things secure. But the process is one in which still the two images that you need for each eye are presented in a way that you construct, using your brain, you construct depth perception. Here's a random dot stereogram. Random dot stereograms were invented by psychologists to study depth perception. And I can't go into great detail about how they're created, but again, the mechanism of creating them still creates the two images you need to construct a three-dimensional perception. And if you look at this image and look past it, like the one I showed you before, you should be able to see a 3D picture emerge out of the dots. And here I see sort of a star shape coming out of the middle of it, as if it was, sand at the beach or something, and this star-shaped object is coming out of the sand. It's an interesting process why these are made, and this gave rise to that retail, magic stereograms printing that you see everywhere. It's the same basic process of taking a random image and generating the two pictures you need to form an object, and it looks completely random in two dimensions. When you look at it just as a picture here, but then when you look past it and you accommodate, your lens accommodates some, you produce the two images you need for each eye to produce a three-dimensional picture. The full mechanism by which stereoscopic vision occurs in the nervous system is really unknown. Obviously, somehow the brain is correlating the two images that are coming in from each eye and figuring out the data about parallax so that it can construct where these objects are in space and formulate a depth perception model so that you can operate on these objects as if they really were there. Well, like many other areas of perception, especially visual perception, discrepancies like this are probably being responded to by networks of cells, so that when a discrepancy occurs, when there's a disparity between the parallax of P and Q there, for example, so when you see the left eye, the two pins down there labeled P and Q. In the left eye, they're seen as lined up. In the right eye, they're seen as slightly displaced. Now that displacement is a cue to how far apart they are, how far away that P is from Q. And probably what happens is there are neurons that respond to a discrepancy like that once the form is established, and then there's a kind of measurement done of some kind that determines how far away P is from Q. Then the three-dimensional model is constructed, includes P and Q and your body in space, and you then have a sense for the distances. But it's probably done by networks responding to disparities, then those disparity neurons are communicating with others that construct the three-dimensional map of space. Again, most of this is unknown. How the brain actually does this, how these neurons actually configure themselves to detect things like this, is just theoretical. It's obvious that there are neurons involved, and it's obvious that it involves firing patterns of the neurons and how they communicate with each other. but the particular firing patterns, the kind of processing that's done by the neurons after disparity is detected is still yet to be discovered. Okay, we've been dealing with depth perception. Now, how do we perceive sizes of objects? Obviously, it involves the perception of, if objects are close to us and farther away from us, we have to figure depth perception into the perception of size. If two objects are in the same plane, it's pretty easy to determine size. It's based on the size they are on the retina. So while you're looking at the objects, the size they are in the visual field of the retina is a clue to how big they are. And when you're looking at these two objects here, for example, are these circles the same size? Well, obviously they are. They look like they're in the same plane. The light is falling on them the same way, the shadows and everything. I don't have any sense that one is in front of the other. And so I'm going to say, of course, they're both the same size. Now we go to the next slide, we're going to have a depth cue that might change your appraisal of the size. Okay, now we got a problem. Putting the truck in the image changes the sense of how far away the circle on the right might be from the circle on the left. So even though it's the same image as there before, throwing a truck in there adds a problem. And now we have to factor in, well, a truck is of a certain size. If this is a real photograph of these three objects, how large would the object in the back be? Well, we really have no choice but to make the object in the back larger because it's farther away. So if we make that inference it's farther away, then the one in the back has got to be larger. Now, I have trouble making it larger because, see, if an object is really, if they were like that, you'd expect them not to be exactly the same size. But and also this is not a very naturalistic looking image. But I have tended, and now that I'm looking at it, I've tended to do that to make the one in the back seem larger. It's got to be larger if this is a true image, because an object that would be that far away is going to have a smaller retinal image, but that's because it's farther away. And I'll get to the details of that in a second. But if it's farther away and it's the same size as the one in the front on my retina, then it must be larger than the one in the front. In general, what we try to do is maintain size constancy. We don't like forms changing their size. We can't imagine, okay, well, if I walk back behind something, it's likely that I can also grow. I can expand somehow. Objects tend to maintain their sizes. They tend to maintain their dimensions. So unless you're dealing with something like a balloon or something, or a basketball, something that's going to change size in a natural fashion, you tend to maintain the size of objects given depth cues. So as objects go back away from you, you tend to maintain the idea that they're the same size. As they come closer, you tend to maintain this idea of the same size, even though they're taking up more or less space in the retina. This phenomenon, this tendency for perception to be biased in this way, is referred to as size constancy. And here you see a schematic depiction of this. When the person is close to your eye, the image on the retina is quite large. When the person is further away from your eye, the image is smaller. But you don't have a perception that the person has shrunk in size because the retinal image is smaller. We tend to perceive size of objects as staying the same, so we tend to think of them being the same, even if they're far away from us and their retinal image is smaller. So there's a relationship between perceived size as a constant relationship between the retinal size times the distance away an object is. So we have a formula in there for calculating, in a sense, the depth perception of objects so that we maintain their size constancy and we don't come to an inference that they're expanding and contracting. Now this can be fooled. You can mess with this perceptual system and produce misperceptions of size, and I'll show you one a little bit later. But in general, we maintain size constancy, and we do that by a factor of essentially calculating the retinal image size relative to the distance that an object is far away. Now there are other cues to size besides the retinal image and the constancy you're trying to maintain, using a sense for the depth perception relative to the size of the object and the size of its retinal image. Here you have a picture of a wheel or a tire. Now if I just show you this tire like this, you probably don't have a clear sense of how large it is. It looks like it's probably, a big rough tire you might see on a tractor or a truck or something. But it's hard to tell. There's nothing around it that gives you a clue to its size. For all you know, it could be a toy tire that's very small. So now on the next slide, I'm going to give you a cue, and you should change your size expectations or your size knowledge given the cue. Okay, how big is the tire now? Now obviously this relative size cue has given you some idea of what the tire size is. Now it's very hard to imagine it being on a big truck or something like that unless you've got a giant baby there. But obviously babies aren't usually that large. At any rate, this relative size cue is a very strong, compelling cue as to the size of the object. Now most of the time our size cues are all pretty consistent with, everyday life. We don't usually see, giant babies or actually very small tires. This looks like it might be a tire, say, for a riding lawnmower or something like that, an object that size, or it can't be a truck and it can't be a small push lawnmower. So it's got to be a tire for something in between. But I clearly have now a sense for the size of the tire because of a relative size cue that I've been given. Whoops, there's another cue. This one's a little different than the baby. Same tire, though. So the same tire image is there. It's now been changed, so there's now another relative size cue. Now this guy can't be a little midget, or a little tiny little person with his tire. You're going to infer that this is an adult, and he's somehow, he's maintaining the tire or something for some very, very large truck. So now the tire size has got to be relative to something much, much larger than we were thinking about before. Now, all these are relative size cues. They have nothing to do with depth perception, size on the retina, or anything like that. These are other objects in the same space, other kind of cues you have to size that comes from the relative size of objects and your memories of them. Okay, veridical perception occurs when your perception matches the actual stimulus situation. So when your size estimations from perception are matching the actual sizes of objects in the world. Now you can have unveridical perception with certain kinds of cues, and stimuli can be constructed so you misperceive the size of objects. And here we have the famous Mueller-Lyer illusion, and this is a very simple illusion in which the stimulus is presented. You have two vertical lines there. The two vertical lines are the same length, and you can check this any way you want to. But when I have associated lines in which your vision is being trained away from the one end of the line or toward it, you will tend to slightly exaggerate and lengthen the line or shrink it some in your perception. And no one knows exactly why this occurs. It's been a great mystery for many, many years why this particular illusion exists. I think it has something to do with how we perceive forms, and we tend to have such an integrity of perceiving forms that we will actually misperceive dimensions because of the way in which our vision has been directed away from or toward lines. It's hard enough to tell that two lines are the same or what their length is. It's more important to know whether they make up a form or not. But that's just an idea that I have, and no one's ever been able to adequately explain why this illusion occurs. Here's another example of the Mueller-Lyer illusion. It's again, the stimulus is presented in a way that the cues direct your attention away from the ends of the line or toward them, or toward the center part of the line. And when that occurs, you definitely have the perception that that line on the left is longer than the one on the right, even though the vertical lines are the same length. Now we have the Ponzo illusion, which I showed you before. That also involves a distortion of perception of size because of depth cues. These two lines, these two white bars here, are the same length. Now the problem is, if they really were there in the real environment, actually in that picture, like this, the one in the back there, which is further away, or depicted further away, would have to be larger than the one in the front here in order for this picture to make sense, to be consistent with perspective. Now, what my perceptual systems do is they say, okay, that's correct. And so because it's spanning the railroad tracks, it must be longer. than the one in the front, which isn't even hardly reaching. It's not even coming close to the railroad tracks. Therefore, the line in the back must be larger. It must be wider. And so my perception clearly is the back one in the back is wider. And that makes the three-dimensional model you're constructing of the world all internally consistent. Now, I presented your brain with stimuli that don't actually exist in the world. If this was actually in the world, I would have to make the one in the back there larger. Suppose I actually was working with, two pieces of wood. Well, the one that's spanning the two railroad tracks in the back has got to be bigger than the one in the front here. I would have to make them bigger in order for that to happen. But here in this, graphic depiction, where I'm drawing in part of it, I don't have to do that. I can fool your brain, and when I do that, your brain constructs the back one larger, just like it would be in the real world. So your brain has a model of how the real world is, how it really exists, how perspective is used to depict the length and size of objects, and it maintains that even in imagery that's not from the real world that we've created just to fool it. And there's no way not to see that one in the back as larger than the one in the front. Your brain is going to do that for you, even if you want it to see it otherwise. Now we have one of the most famous examples of how size and depth illusions occur. This is the Ames room, and this is a remarkable invention. There's a movie I have at the course website. If you play the movie called Room.mov, it will give you a nice demonstration of how this is constructed. I'm not going to explain this in detail because the movie does a good job of doing that. But basically the room is constructed in a way that fools your size and your depth perception because you expect rooms to be a certain configuration. Your brain expects that. It makes the size of the objects conform to its expectation. And it makes the objects in the room, like the little boy and the little dog there, actually change size to match your expectation for the depth perception of the room. It's a remarkable thing. It really is an amazing thing that your brain will do this kind of manipulation of your perception just to make everything internally consistent. And you have no control over it. You can sit there, and I've tried this looking at that movie over and over and over again, trying to perceive the objects correctly, and I can't do it. My brain wants the world to be a certain way, and I'm just the victim of its processing. And finally we have the moon illusion, probably the most famous illusion that involves depth and size estimation, and one of the greatest mysteries of all time. It was noted even back probably in the Middle Ages that the moon illusion was an illusion. There was a problem with how we perceive the size of the moon. Basically, when you go out and look at the moon, and go out and look at a full moon, when it's just rising, when the moon is just rising on the horizon, it looks very large. And I remember, driving along in the car when the moon's coming up thinking it's just gigantic. It's often depicted this way also in artwork. You'll see scenes, landscapes in which the moon near the horizon is depicted as very large. Then as the moon goes up in the sky, it appears to get smaller, very dramatically smaller. But if you were to go out and take a photograph of the moon at both times and look at the photograph later, you would see that the moon at both times is exactly the same size. Somehow your brain is trying to figure out how this object, the size of this object. And no one's been able to adequately explain why we do this in such dramatic form for the moon. Probably has something to do with the fact that at the horizon there are depth cues, and we know that the moon is behind objects that are very, very, very far away from us. And if the moon is that far away, it must be very, very large. And so our size estimation, our size perception, is that the moon is very, very large when it's near the horizon. But as the moon goes up in the sky, as it rises up off the horizon, we don't have those cues that it's behind objects that are far away. For all we know, it could be relatively close to us, like a light hanging up there in the air. And our estimation then of size, it makes the moon much smaller. And it's a remarkable thing that it happens. You can go out and test it if you want to. Go out and take photographs, or another way to do it is to go take a ruler or just a pencil, and when the moon is at the horizon, hold the pencil out arm's length so it's perpendicular to your vision, and have it cover the moon, and then mark on the pencil where the size of the moon is relative to your arm length. And then later, when the moon's up in the sky, do the same thing. So hold up the pencil, and you'll be amazed that the moon in the sky is the same size, takes up the same pencil, area as it did when the moon was at the horizon. Yet your perception, your internal representation of the world, made the moon at the horizon much, much larger. Again, nobody knows exactly why this happens. It's obviously related to size and depth perception and how your brain is trying to figure all this out. And it's a kind of illusion. Fortunately, no one has to interact with the moon very much. That sort of misperception is not going to cause you any trouble. And generally these don't, because most of the time these big differences between perception in the real world are in domains that psychologists set up for you as artificial things that they show you in their laboratories that don't exist in the real world. Presumably there are some perturbations that exist, slight ones in the real world, but most of the time what your brain is constructing is a true representation of the world. It's not a very false one. And it's only when psychologists tweak it and screw around with the perception that you make these kinds of errors. Most of the time things are going along fine. I think in general also it highlights the way in which the brain is accommodating, the way in which your brain is constructing your perceptions. And that's not something that I have a really sort of clear internal idea of. I don't know that my brain is constructing all these size designations for me. I don't know it. I'm just observing it. I use that information, or I use its construction, but I don't have a sense of what it's doing. The same is true for things like color and other kinds of visual perception, and also other kinds of senses and hearing and taste and so on. All these things represent the brain's construction of the world from information that it gets from the world, but sometimes it gets incomplete information or inconsistent information, and it always makes a perception. It never sort of reads out, well, I can't perceive the world right now because things are too confusing. It always makes some kind of accommodation, some kind of perception, so that you have a model to base your movements and your other perception on. Fortunately, I've never been in a position where I actually had to go out and grab the moon or touch the moon. If somehow the moon was important for me to touch, I think I'd have a hard time doing it. Mostly because my brain isn't giving me the correct information about it. But pretty much everything else in my environment, my brain model is matching the real environment, and I don't usually have a sense of, falling down stairs or something because my brain has missized them or misjudged the depth.